Right now, behind your eyes, there is a color you have never seen. It is not on your screen. It is not in the rainbow. It is not in any sunset, any paint can, or any star in the sky. It is a blue that is darker than black. And in a couple of minutes, you are going to see it. Here is the thing about color that almost nobody gets told. You probably think of it as a property of stuff out in the world. Grass is green. Blood is red. Light arrives with a wavelength, and the wavelength is the color. That is almost right, and it is wrong in a very specific way. Color is not something light carries. Color is a verdict your brain issues about light. And a verdict can be pushed into saying something that could never be true. To see how, you need to know how the verdict gets made, and it is simpler than you would think. At the back of your eye are three kinds of color sensor. One leans toward reddish light, one toward greenish, one toward bluish. But your brain never sees those three numbers on their own. Before the signal even leaves your eye, it gets rewired into a tug-of-war. Two ropes. On the first rope, red pulls against green. On the second, blue pulls against yellow. And running alongside them, a third channel that ignores color entirely and tracks only brightness, black against white. Every color you have ever seen in your life is a position on those three ropes. Orange is red winning slightly, yellow winning strongly, brightness high. That is the entire system, three numbers. And look at what that makes impossible. A rope cannot be hauled hard in both directions at the same time. So there is no such thing as a reddish green. There is no bluish yellow. Try to picture one right now. You cannot. And not because your imagination is weak, because your brain has nowhere to put the answer. But here is the crack in the system. Those sensors get tired, stare at one color long enough, and the team hauling on that end of the rope wears out. Then take the color away, and the rope snaps back the other way. That is an afterimage, the floating ghost you get after a camera flash, always in the opposite color. Normally that is just a party trick. But if you point a tired rope at exactly the right surface, at exactly the right moment, you can force your brain to hand back a verdict that has no physical answer. A color with no wavelength and no place on the rainbow. Let us do one, right now. Turn your brightness up if you can. A dim room helps. In a moment, the screen will fill with yellow, with one small black dot in the middle. Put your eyes on that dot and keep them there. Do not glance around. This only works on the exact patch of eye you hold still. 20 seconds. Then the screen goes black, and you keep looking at the same spot. It is completely harmless, and it fades on its own in a few seconds. Here we go. Eyes on the dot. Hold it there. While you do, this is what is happening. The yellow end of your blue-yellow rope is being flooded, and it is quietly giving up. You cannot feel it. There is no sensation of a sensor getting tired. 10 more seconds. Keep them still. The yellow in front of you is already starting to look slightly less yellow, and that is your own eye backing off. 5, 4, 3, 2, 1, now, black. Do not move your eyes. Keep looking at the same spot. There it is. A blue shape, sitting in the dark. If it is faint, you moved your eyes. And notice something about it. It is not glowing. It is not lighter than the black around it. That is the impossible part, and it is worth slowing down for. The black on your screen is the darkest thing your screen is able to make. Almost no light is coming out of it. Your brightness channel was reporting the floor. Nothing here. This is as dark as it gets. And at the very same instant, your blue-yellow rope was reporting blue. Those two readings together describe a color with no counterpart anywhere in the physical world. A blue that is as dark as black, and still, unmistakably, blue. Vision scientists have a name for that family. They are called Stygian colors. Stygian blue is the famous one, and you have just seen it. And you cannot get it any other way. A screen makes color by adding light, and this color needs a hue with no light at all. No paint can mix it. No surface can reflect it. No camera has ever captured it. It is not rare, and it is not hidden. It simply does not exist outside a nervous system that has been briefly knocked off balance. Now run the same trick backwards. Stare at a strong green, And then, instead of black, look at white. White is already the brightest your screen goes. There is no headroom left. But your red-green rope has just snapped hard toward red, so your brain lays red on top of maximum brightness. What you get back is a red that appears to glow. Not a red thing that is lit up. A red that seems to be giving off light of its own, out of a flat sheet of paper. Those are called self-luminous colors, and they are why people describe afterimages as burning. That red reads as brighter than the white it is sitting on from a page that is not emitting a thing. And there is a third kind, which breaks a different rule entirely. Stare at a strong cyan, that swimming pool blue-green, and then look at a strong orange. The orange comes back more orange than orange, more saturated than any orange a screen, a printer, or a laser is able to make. Physically, saturation has a ceiling. A single pure wavelength is the most saturated light there is, and nothing beats it. But your visual system has no ceiling because it is not measuring purity. It is adding up votes. Push the votes past the end of the scale, and you get what is called a hyperbolic color. Hyperbolic orange looks, roughly, like somebody turned orange up past the last number on the dial. So, a fair question. If tiring out a rope can shove you past the ends of the scale, could you get a rope to pull both ways at once? Could a person actually see a reddish green? In 1983, two vision researchers tried it. They built a rig that tracked a volunteer's eye and moved the picture to match, so the border between a red stripe and a green stripe stayed frozen on the exact same patch of eye, no matter how the eye moved. Held that still, the border between the two stripes dissolved. And some of those volunteers reported a single color, at once red and green, that they could not name and could not describe afterwards. Not brown, not olive, not a mixture. Both. That one is still argued over. A team reproduced it in 2010 under carefully controlled conditions. Other researchers say what people actually see is the two colors flipping back and forth too fast to tell apart. Nobody has closed the case, which I find quietly wonderful. There is an open scientific question about a color, and the only laboratory it can ever be settled in is the inside of somebody's head. The colors you saw today, though, are not in dispute at all, and they point at something bigger than a trick. Think about what a color actually is now. Not a wavelength, not a thing light carries around with it. A color is the answer your brain gives when it compares three running totals. That is all it has ever been, which means the space of possible colors is not the space of possible light. It is the space of possible answers. And the answer space is bigger. There are combinations your eyes can report that no photon in the universe is able to cause. The rainbow was never the full set of colors. The rainbow is only the part of the set the physical world happens to be able to build. The rest are still in there, sitting in the wiring, waiting for somebody to stare at a yellow rectangle for 20 seconds. So the next time somebody tells you that black is as dark as it gets, and you want to know how a color could possibly be darker than nothing at all, well, then you'll know. And if you want the other half of this story, the one about why your eyes can see green absolutely everywhere but not one mammal on Earth is able to wear it, go and watch the video on green mammals next.